All right, good afternoon, everybody. We're just going to give it another minute or so, let people join in, and then we'll get started here in just a bit. All right, while everyone continues to join, just wanted to reiterate the message that was shared in the chat. So the recording will be shared after the event is over. So everybody that registered is going to have access to that recording. And then also, if you happen to have any questions during the webinar, feel free to use the Q&A option to send in your questions, and I'll be happy to address them. Just give it one more minute before we get started. All right, we'll go ahead and kick it off. So to everybody that's joined, welcome to today's webinar where we'll be covering Tater tokens. This is going to be an introduction to Windows access tokens, how they work, a little bit about them, and then how they can be leveraged for privilege escalation in a Windows environment. So before we dive into it, just introduce myself. My name is Max Andriaki. I go by Atomic Chonk on social media. My role here at SpectreOps, I'm an associate consultant in adversary simulation. Areas of research that I've dived into recently include Active Directory, social engineering. I have a lot of experience with both vishing and phishing. And as of late, I've been jumping into the AI craze, specifically exploring natural language processing and things having to do with text and language in artificial intelligence. A little bit about me, I am a husband to my better half. I'm also a quirky dad to these two living furry potatoes here on the right side of your screen. I am also a cat servant to the gremlin on the bottom right-hand side of your screen. I'm a tattoo collector and also a runner. So if at any point during the day you want to distract me, these are the topics that you can definitely approach me with, and you will have my full attention. So a brief breakdown of what the webinar will entail. First, I'll go into an introduction to Windows access tokens. Then I'll cover how you can use these tokens in privilege escalation, also known as the potato attacks. And last but not least, I'll go into a little bit of detection development, how to detect these attacks. So without further ado, an intro to Windows access tokens. So what is an access token? An access token, per Microsoft, right, is a security mechanism in Windows built to give a user access to specific resources. So the way I like to describe this to folks that maybe are new to cybersecurity or it's just a foreign concept to them, it's that an access token is like a key that can open specific doors to areas in a building that contain useful items or information, but it doesn't open every single door. The example I have here on the right-hand side of the slide is that we have a corgi here. She has a key, and she says, I have access to the sheep's pen and the chicken coop and the pig pen, but not to any of the crops. So she can access certain valuable resources, but not all of them, because allowing that extensive access could be detrimental to the organization's security. So the Windows Security Reference Monitor, or the SRM, is the gatekeeper when it comes to tokens. And so what the SRM does is that it ties identities in Windows to tokens and then determines whether or not it'll allow or deny those identities access to specific resources. An important note is that tokens aren't the only part of the access check that Windows performs, but they are a key part of it, and that's the part that we'll be covering today. So there's actually a lot of information in an access token, and I'm going to touch on most of these briefly. So SIDs are security identifiers. They are alpha or numeric values that are globally unique in the Windows ecosystem and allows you to differentiate objects from each other. And so within an access token, the SIDs that are contained in there are a user account SID, so the user account that that token is tied to, a SID identifying the current logon session, and this is going to be important later on, and I'll highlight points like this that are going to be important throughout the presentation. Also, the SIDs of the groups that the user is a member of. The owner SID, and this was really interesting when I was performing my research. So the user account SID and the owner SID aren't necessarily synonymous. The owner SID is what is used when the user creates an object or uses the token to create an object. Maybe that SID is tied to a local administrator privilege that that account might have. That is what's used to create the object, not just the user account SID itself. Also, we have the primary group SID. This is just among the groups that the user is a member of. One of those groups is designated as the primary, and that SID is put into that slot. And also restricting SIDs, so objects that the user explicitly cannot interact with are included in that token. Next, when it comes to token attributes, so it'll be the type of token, primary impersonation, and we'll get into that a little bit later. Also, the source of the access token. So for example, if it came from LSAS, right? Pretty much this source is designated by any process that can call NT create token, that API call. Any process that can call that can create a token. That source is specified within the token. And last but not least, current impersonation levels, which we'll get into a little bit later. Some additional information that's included in the access token is a list of privileges held either by the user or the user's groups. And the way Windows likes to do this is that it's the least common denominator of those two is essentially the list of privileges that that token has. Also, the DACL that the system uses when the user creates a securable object without specifying a security descriptor. So that's a lot of buzzwords. What does that mean? All right, so a DACL is a discretionary access control list. And this is a string of letters, essentially, that determines what permissions a user has over an object, right? Read, write, execute type of thing. If a user creates an object and doesn't specify a specific DACL, then there is a DACL contained within the token that is used whenever that user creates objects. It's just the default DACL that gets applied to objects. And last but not least, other statistics that I'm not going to dive into today. So access tokens are given to users as they log into a system. So here we have a depiction of the Windows Security Reference Monitor, or the SRM. And here we have user one, log on session one. So user one is logging on to this system. The SRM is going to issue a token to that user, say, here's your token. And that user is logged onto the system. Whenever the same user goes to log on a second time, they are going to be issued a separate token, or a token with a unique identifier. So for a given logon session, all user tokens will have the same authentication identifier. But if that user authenticates twice to the same machine, the SRM is going to generate different authentication identifiers for different tokens. So here you can see user one logon session one has a token identifier of ABCD. User one logon session two has a token identifier of EFGH. So this means that tokens are tied onto specific logon sessions, not specific users. And if you remember, the token contains an ID identifying the current logon session that it is tied to. So this means that a user or a logon session can have multiple access tokens associated with it. However, an access token or a single access token cannot be linked to multiple logon sessions. So obviously this is theoretical. Processes aren't made out of potatoes and food ingredients, right? But this is a depiction of the fact that the access token you receive when you log in is tied to processes you create. So if you create a process in the user's context that you are in after you've logged on, that process will contain a copy of the access token that that user received upon login. So you see all these DLLs, right, that the process is referencing, but also it's going to contain in memory a copy of that access token that it received, that the user received when the user logged in. All right, so primary tokens and impersonation tokens. So primary tokens are owned and used by a given process. And in order to create one and associate it with a process, escalated privileges are required. For an impersonation or a thread token, so this is a token that's been created to capture the security information or context of a client process. And it allows a server to impersonate a client process. And there are multiple levels associated with impersonation. Specifically, there are four. It goes from anonymous all the way up to delegation. Anonymous seems a little bit fruitless, right? Because you can't impersonate the client. Identification, you can get the ID and privileges of a client, but not perform actions. So if a server is trying to get the context of what user is trying to access it, for example, that's where an identification impersonation level would be useful. But again, it can't carry out actions in the context of that user. Next, you have the impersonation level, which is a little bit redundant, but it allows a server to impersonate a client security context on the local system. And then a delegation impersonation level allows the server to impersonate a client security context on remote systems. So how can we use all of this information and how can we use these objects to perform privilege escalation? So we're going to cover a couple of fundamentals in the context of privileges and privilege escalation before we dive into the actual mechanics of performing these attacks. So a privilege is essentially what a user account can do in a Windows environment. So here you can see a very extensive list. Granted, most of these are in a disabled state, but here you can see a very extensive list of privileges that could be associated with a user account. Of these, some of the useful ones that are typically used for privilege escalation are like SE backup privilege. The one that we'll be touching on today is going to be SE impersonate privilege, so on and so forth. So like I foreshadowed, SE impersonate privilege. So what treasures lie within the SE impersonate privilege? So it allows a user to impersonate a client after it's authenticated. Usually local administrator accounts and local service accounts have this privilege by default. Also, services that are managed by the Windows Service Control Manager and some COM servers are at times also assigned this privilege. So what's a COM server? So COM stands for Component Object Model, and it is any object that provides services to clients. So that's a very generic definition by Microsoft, right? So I kind of break it out a little bit here. Server is a little bit confusing. The way I like to think of it is that it's a piece of code that can be imported by an external program through a standardized interface. So a DLL could be a COM server. And COM class objects are identified by a class ID or CLS ID. And I'll explain a little bit more about that in the coming slides. So what's DCOM? DCOM is essentially COM with a longer wire. And so it allows COM objects to communicate across networks. What it does is that it enables RPC between objects on different endpoints. And what's important to note is that DCOM objects typically run in a privileged context. And that's actually what we're going to be targeting when we perform our privilege escalation later on in the webinar. So class IDs. Class IDs are globally unique identifiers or GUIDs that identify COM class objects. For example, if you have two similarly named COM class objects or two of the same type of object, you don't want that collision. So you're going to use a globally unique identifier to differentiate them. The information associated with a class ID is stored in the registry. And this is the information that is used by a COM handler to return information about a class when it is in a running state. RPC. So RPC is a protocol. It's known as remote procedure call. And essentially it allows programs to communicate between each other. That can be on the same host or it could be across different hosts. What it specifically does is that it allows a program to call functions within another program as if that function was local to the calling program. So without further ado, Tater time. So what are the potato exploits? The potato exploits are a group of privilege escalation techniques, some of which abuse the SE impersonate privilege and were developed over time as mitigations were implemented by Microsoft. So I like to describe this as a back and forth between the research community and Microsoft. You had hot potato, which was the first potato exploit that was identified. Microsoft implemented mitigations to that in an effort to work around those mitigations. Later potatoes were developed, rotten potato, so on and so forth. It's been this back and forth. Right now, I like to say that research has the upper hand. We have God potato, which unfortunately I will not be covering today, but I will touch on later on in the presentation. So yeah, it's this back and forth between the security and research community and Microsoft. But today, what we'll be covering is rotten new generation, rotten NG, juicy, and rogue potatoes. So rotten potato NG, the reason why I chose specifically the new generation as opposed to the original, so the original was reliant on Metasploit and Meterpreter for its callback communications. I wanted to present something that was kind of like C2 agnostic or callback agnostic. So new generation allows you to modify how you want, or what process you want ultimately executed in that privilege context. So rotten potato was identified 9 years ago in 2016 by Brain Machine. Its strengths are its stability and its use of DCOM to trigger authentication. And its weaknesses are that it is not functional in systems that are beyond Windows 10, 18, or 9 or Server 2019. So the basics with rotten potato, what it does is it coerces NTLM authentication from an NT authority system level account, which in this case is going to be DCOM, to a TCP endpoint that we control. And so what we're going to do actually is that we're going to intercept that authentication attempt to locally negotiate a security token for that DCOM account. So we're going to leverage that DCOM account's privilege, but in turn get a token for our context. And then we're going to impersonate that token that we just negotiated because one of the requirements is that the current account we're starting from has that SE impersonate privilege enabled. And the other requirement is going to be that we have control over a TCP endpoint, which can be that same host, or it can be an attacker system, which is how I'm going to present the attack chain. So the first thing you actually want to do is if you go into the source code for the rotten potato NG repository on GitHub, you want to modify the intended command to execute. So here you can see that CMD path is going to launch CMD with arguments. If you want to have a callback to your system, let's say you have like netcat on the system where you know that you can get netcat on the system and that's what you want to execute to a listener that is on your attacker system, you can modify it to do that. So we're gonna set up the scenario. So you have a low privilege session established on this .1 system, and then you're going to set up a listener on the port that you specified in that code. So let's say you want it to call back using netcat to 4443. That is the listener that you set up. You're going to enumerate the privileges of the account that you've compromised. It is a service account. And it does fall in line with what's traditionally expected with service accounts, which is that SE impersonate privilege is enabled. And we also control a TCP endpoint on the network, our attacker system, so we can proceed. So what we're going to do is we're going to upload rotten potato NG to the target system, and we're going to execute it. And for anybody that's run these command or run these exploits and like hack the box or whatever, it's pretty quick and concise, right? You just like run the command and then it works. But there's actually so much happening under the hood. And that's the whole reason why this presentation came to fruition. I had the shower thought of why does this work? And we're going to discover this together. So when you execute the rotten potato binary, what it's going to do is going to trick decom, which if you recall is running in a privileged state, is running as NT authority system, into performing NTLM authentication. What we're then going to do is we're going to use an API call to tell a COM object that we want to fetch an instance of a bits object. So if you have run a Windows update on your system, you have used bits. It is a background service that is responsible for file sharing, file upload and download. So we want to load this bits object and load it locally on port quad 6. And what's going to happen is that Rotten Potato is going to relay that request from the port quad 6 to port 135, which is an RPC interface, to make sure that all the RPC responses are crafted correctly into the proper format. And what's going to happen is that this port, the 6666, is going to operate as an adversary in the middle point for this NTLM authentication that's going to take place. So here on the left, you have your COM object, which is decom. On the right, you have port 135, which is your RPC interface. At the top, you have rotten potato new generation, which is sitting on port quad 6. And so the NTLM authentication kicks off. So decom is going to establish connectivity with the RPC server interface, again, through that port quad 6. And it's going to send an NTLM type 1 or negotiate message. While it's on its way, Rotten Potato is going to extract the NTLM blob. And what it does is it's actually looking for a series of magic bytes that spell out the NTLM SSP header to identify where it's going to rip out that NTLM blob from. It's going to extract it. And so what it's going to do is allow that type 1 message, again, to continue on to the port 135 RPC interface. And in the meantime, Rotten Potato is going to pass its NTLM blob that it's extracted to accept security context. Accept security context is going to respond to Rotten Potato with a type 2 challenge message for the NTLM blob it provided. And the RPC interface is going to do the same with the COM object. And what's actually going to happen is that Rotten Potato is now going to place that NTLM blob from the type 2 message that it negotiated into the envelope or the casing of the type 2 message that was taking place between decom and RPC. And the reason why this happens is that it's forcing the NT authority system or decom account to authenticate with the values that Rotten Potato negotiated for the account that we initially compromised. So it's crafting a token for us and not for that RPC decom interaction. Then decom is going to respond with a type 3 message. We're actually just going to grab that and pass it on to accept security context ourselves, and we'll receive a reply. And then we'll pass that reply over to impersonate security context, which is going to ultimately allow us to obtain an impersonation token. So now there's going to be an impersonation token for NT authority system available on that host. And since we have SE impersonate privilege, we're going to be able to impersonate that token, and it's going to execute the command that we originally placed in the source code. So in this case, it would be like netcat.exe calling back to the .2 on 4443, and it's going to be in a session in the context of NT authority system. So we now have a privileged shell on the target box. All right, so that was a lot of NTLM and authentication and all of that. But now we get to move on to the later generation, which is Juicy Potato. So Juicy Potato was disclosed 7 years ago in 2018 by Decoder IT, and he has done a lot of fantastic work on the potato iterations that have come afterward, and he collaborated with Jutro on this. The strengths of Juicy Potato, I would describe it as an advanced rotten potato. So you have, instead of being confined to having to use bits and port 6666, you actually have your choice of class ID and COM server to abuse. and we'll get a little bit more into that in the next slides. Unfortunately, its weaknesses are also Windows 10 1809 and Server 2019. It is rendered obsolete by the patches that were released in these operating systems. So, like I described, Juicy Potato is built upon the logic of Rotten Potato. So, Jutro and Decoder IT, or Andrea Perini, identified an instance where bits was disabled and port 6666 was not available, so they were pretty handcuffed as far as what they could do. But their research led them to identify several COM servers other than bits that could be abused. And so the prerequisites for being able to use Juicy Potato are control over a TCP endpoint and that SE impersonate privilege on the current account we're starting from, similar to Rotten Potato. But also you need a COM server that's instantiable by the current user. You also need this to implement the iMarshal interface and run as an elevated user, and I'll get a little bit into that. So you're going to establish a low privilege shell on the .1 like we did last time. You're going to enumerate your privileges, again, in line with it being a service account and following what's expected. The MS SQL service account shows that SE impersonate privilege is enabled. You also control a TCP endpoint on the network as you did previously, so we're able to proceed. You're going to set up a listener on your port of choice. Again, like we did with Rotten Potato, you have to do a similar modification to Juicy Potato in its source code to determine what executable or what binary you want executed in that privilege context. You're going to upload the binary to the target system. And then upon execution, again, Juicy Potato is going to trick DCOM into performing that NTLM authentication. So a lot of the mechanisms are the same between Rotten and Juicy. The only difference is that you, instead of having to specify bits and that 6666, you can actually specify a COM server more or less of your choice. So the developers of Juicy Potato actually created this web page where you can identify the different class IDs for each Windows operating system. And you can see on the bottom screenshot what service it is, what the class ID for it is, and it's a little bit cut off there on the end, but you can see what context or what privilege level it runs in. So for the purposes of this walkthrough, we're going to use a shell HW detection object, and we're actually going to specify port 1337, and that's going to be our adversary in the middle point for that NTLM extraction and negotiation alongside the DCOM RPC interaction. So this is what it would look like if you ran it locally. So if you run Juicy Potato, you have local port 1337. You want it to run cmd.exe, and then you specify the class ID of the object that you want it to instantiate as the adversary in the middle point. You see at the bottom of the screen there that it spawned a cmd.exe process in the context of NT authority system. So again, like I mentioned previously, anybody that's used these, you just run a one-liner and then boom, you have privilege escalation. But as you can tell, a lot's going on under the hood. So as you can see, the adversary in the middle point is at 1337 we specified. It's relaying between DCOM and RPC, and it's going to lay the groundwork again for NTLM authentication to take place. I've taken that DCOM RPC set of slides that we went through previously and just kind of consolidated it. The Fox Security folks actually built this diagram, and I think it's a really good depiction of just a concise NTLM authentication interaction that ultimately results in an impersonation token being generated. So Juicy Potato is going to spawn the process you indicated in the original code with the use of its NT authority system token that it produced. So last but not least, and probably one of the more complicated potatoes to walk through, is Rogue Potato. Rogue Potato is 5 years old. It was also disclosed by Decoder IT alongside Splinter Code. And its strength is that it bypasses the Juicy Potato patch that rendered it obsolete. I don't have a weakness listed here, but in more of the research and reading that I've done, I would say that one of the weaknesses of Rogue Potato, at least historically, was that it would require a second system, and you'll see why when we go through the walkthrough. But after talking to a few folks and actually like software engineers, that requirement might not be necessary anymore because of the way LSA works. But we'll get into it. So a little bit of groundwork laying. So OXID queries. OXID is an abridged form or format of object exporter identifier. What it is a 64-bit number that identifies an object exporter within an object server. So again, Microsoft lingo, but object exporters can be processes or threads in an object server, which is essentially an execution environment. Object exporters are callable using RPC interfaces. So just make a note of that as we go forward. So what's an OXID resolver? An OXID resolver is a service that runs on every machine that supports COM or COM+. It has two primary functions. One is that it stores, the RPC string bindings that are necessary to connect with remote objects. And two, what it does is that it sends ping messages to remote objects for which the local machine has clients, and then it receives those ping messages back for objects running on the local machine. So think of it as, how you have DNS resolution and there's this like one entity that shows you where to go. This is essentially the same thing, but for OXID and for processes and objects within the Windows ecosystem. So it is a part of RPCSS and is bound to port 135, and a different port cannot be specified, which will be important for the privilege escalation process. The other part is that OXID resolutions are typically authenticated, and I have diagrams that explain all of this. So to explain the RPCSS and OXID resolution process. So here we have two programs that are essentially trying to communicate with each other. And what's going to happen is that program 1 is going to reach out to RPCSS and say, hey, I have a message for program 2. Can you get this to them? RPCSS doesn't just innately know where program 2 is, so it's going to interact with the OXID resolver and ask where program 2 is and authenticate to the OXID resolver to perform that action. The OXID resolver is going to return the route to program 2, and RPCSS is going to follow that route, get to program 2, and authenticate to program 2 as well. And once it's confirmed that route, it's going to pass the route back to program 1 and say, hey, this is the route to get to program 2. Here's the route for you to be able to send your message, and program 1 is going to be able to communicate with program 2. So how do we abuse this? So the potential for privilege escalation was identified, again, in follow-on research for Juicy Potato. Once Juicy Potato was rendered obsolete, they were actually deep diving into WinRM and actually identified this privilege escalation path instead. So what Rogue Potato does is it actually stands up a fake OXID resolver and then uses OXID server procedures to generate a system impersonation token. Really what it does is you stand up a fake OXID resolver and it gives directions to RPCSS to a named pipe that we control. And that's where we're actually going to steal RPCSS's token, and it's going to result in a two-step privilege escalation process. So here we have our fake OXID resolver and program 2, which is the named pipe we control. And when RPCSS asks, hey, how do I get to program 2, hypothetically, the fake OXID resolver is going to respond and say, yes, this is definitely the route to the program you're looking for, when it's really a named pipe that we control. And RPCSS is going to reach out to that named pipe and authenticate to it. And now we have an NT Authority network service token that we can impersonate. Once we impersonate that NT Authority network service, we can access the tokens that are cached in its memory, and we will gain access to an NT Authority system token, which will result in the ultimate privilege escalation. So what did we just cover? What Rogue Potato does is that it abuses OXID resolution, to achieve a two-part behind-the-scenes privilege escalation from basic user to network service to then system. The prerequisites are control over a TCP endpoint separate to the target host. Again, there is further discussion on this that I won't be covering today, which is a little bit debatable about the separate piece of that. But originally, when this was researched, you needed a separate host in order to perform this attack. And then also SE impersonate privilege on the current account you're starting from. So you have a low privilege shell established. You enumerate your privileges, confirm you have SE impersonate privilege. You control a separate TCP endpoint on the network, so you're able to proceed with the attack. You're going to upload Rogue Potato. Now here's where it gets tricky. If if you remember, you cannot modify the port for RPCSS in Windows. So in order to stand up the fake OXID resolution, you're actually going to have to point the traffic to port 135 on your system or in your attacker system. And then that redirection is going to point to the rogue OXID resolver that is running on the victim system on 1337. You're also going to have a listener listening and ready to catch the privilege escalated shell. So this ugly one-liner is how you would execute rogue potato. And so we're going to break down the parts of this. So the TAC R is going to be the remote IP for redirection, which is the attacker system that you control. You have the command to execute with TAC E. So here we're executing netcat, pointing to the attacker system on port 4443, and we want it to execute cmd.exe. And then lastly, the TAC L is going to specify what port the rogue OXID resolver is running on the target system. So an OXID query is going to be sent to port 135 on the attacker system. That redirection is going to kick in and point to 1337, port 1337, on the target system where that fake or rogue OXID resolver is running, and ultimately going to point RPCSS to the name pipe we control. So rogue OXID resolver is going to respond to the query with a procedure known as resolve OXID2. That response is going to specify that named pipe using a validation bypass. So that bypass is actually as simple as using slashes in the wrong direction to specify what named pipe you want it to go to. And it's going to escalate to NT Authority Network Service. Using that NT Authority Network Service privilege, there's a token stealing feature in the binary. So it's going to open the RPCSS process and attempt to impersonate the system token contained in the process's memory and launch that process. The reason why this works is because NT Authority Network Service can be tricked into writing a named pipe over the network. So it's going to impersonate that pipe and access the tokens contained in RPCSS's memory. At this point, you're going to catch a system shell on port 4443. So what are some mitigations for the potato attacks? Patches are for more than pumpkins. So rotten potato and juicy potato were rendered obsolete in environments that were patched beyond Windows 10 1809 and Server 2019. As of right now, the potato that reigns supreme is God Potato. It works in Windows 11 environments and the way it actually functions. So whereas with Rogue Potato, you need a separate system and there's this deviation of OXID resolution and whatnot, what Rogue Potato or what God Potato actually does is it modifies the table in memory of RPCSS and modifies it and points it to the named pipe that you control. So instead of having to reroute all of this resolution, it just modifies the table and just tells it, hey, go to this named pipe. And that's how it achieves the privilege escalation that way. It points to the named pipe, we grab that token, and again, it's that two-step privilege escalation process. Fry NTLM authentication. So rotten potato and juicy both exploit NTLM authentication. So if it's disabled, the attack won't work. So use Kerberos instead. I know this is a very controversial topic. When is Microsoft going to get rid of NTLM authentication? We have legacy systems that rely on it, etc. But objectively, these attacks would not work if NTLM authentication was not in the environment. And last but not least, as a prior threat hunter, a prior blue teamer, taters don't grow on suspicious trees. So implementing detection logic for anomalous processes, especially ones that spawn processes with high integrity like system or network service, you have some weird binary that's spawning processes in elevated context, something that you can build detections for and catch sooner rather than later. So that is all I have for you today. Thank you for coming to the webinar. Again, I'm Max Andriaki. I go by Atomic Chonk on socials. I also have a blog, corgicore.com. If anybody has any questions, I'd be happy to address them. Also, we'll share some of these resources later on after the webinar. right, so I see a question here from earlier. I apologize for not seeing this sooner. So the question is, are tokens only for user accounts, or can computer accounts or other resource accounts be granted a token? That is a great question. The extent of my research has only been for tokens with user accounts. I haven't encountered situations where computer accounts or resource accounts are granted a token. That's not to say it's not possible, but the extent of my knowledge on this one just extends to user accounts. All right, any other questions? All right. Well, if that's it for questions, like I said earlier, this recording will be available after the event. I want to thank you all for joining, and feel free to reach out on socials if you have any further questions or areas that you want to discuss regarding potatoes. Thank you.